Velocity. The speed of an object is measured by the distance traveled divided by the time it takes to travel that distance. And speed is a scalar measure, but when we add a direction to the speed, it's now called velocity. The velocity of boats and planes is affected by the velocity of the current and the wind. To determine the actual velocity in these situations, we must add these velocity vectors together. So let's look at an example. A canoeist is trying to cross a river that is 800 meters wide. She can paddle at a speed of 4.5 kilometers per hour in still water, and the current is flowing at 2.5 kilometers per hour. If she steers the canoe perpendicular to the current, what is the resultant velocity? So first up, let's start by drawing a river. And we'll say that this is 800 meters wide. I'm going to go ahead and convert this into kilometers right now so that I know that it is in the right unit for later. The velocity of the current is flowing at 2.5 kilometers per hour. So I'm going to say that just for the sake of this diagram, doesn't really matter, that this is downstream. So this is 2.5 kilometers per hour, or this is a vector. So I want to make sure that I don't get confused that this is a speed, whereas 0.8 is a distance. The question tells me that she's steering the canoe perpendicular to the current. So that means that she's going to go this way directly. I know that I want to add these vectors together, so I need to set them up tip to tail. So I'm going to put it right there so that I have them tip to tail. This will give me my resultant vector. Okay, so now that I know that she's going 4.5 perpendicular to the current, now I can find my resultant vector x. This is just a straight up Pythagorean theorem problem. And so I can figure out that 4.5 squared plus 2.5 squared all square root is equal to 5.15 kilometers per hour. It's always good to double check and think about whether or not the resultant vector speed should be greater than or less than her heading speed. So she's going 4.5 kilometers per hour. Is the current helping her or hindering her in this case? And it is going to be helping her. It's going to be pushing her downstream a little bit faster. So it makes sense that she's moving a little bit faster. All right, at what point down the river will she land? Well, in order to figure this out, I need to know this angle here so that I can find this distance down the river. So I'm going to use right angle trig. Tan of that angle is equal to 2.5 over 4.5. And I can calculate to figure out that that angle is 29 degrees. So she's been pushed 29 degrees downstream. I'm going to redraw my diagram. And I know that this is 800 meters. This is how far downstream she's gone. This is her line of motion, and this is 29 degrees. So from here, I can just use tan again, tan of 29, the distance she's gone downstream, and the distance across the river. So these are all distances now, no vectors. I can rearrange to solve to find out that this is 443 meters downstream. Let's say she actually wants to get across the river at that particular point. She wants to get right across the river right at that point there. So she wants her resultant vector to be right there. Well, I know that my current vector is still 2.5 kilometers downstream, but I want her to end right there now. So I'm going to put it pointing at my final destination. Now she's going to have to move. She's going to have to aim herself upstream in order to compensate for this. And I know that I need to go that way because I need to make tip-to-tail vectors. So there's my resultant vector, my goal to go straight across the stream. I can only paddle 4.5 kilometers per hour, I need to compensate for the 2.5 kilometers per hour push going downwards. And the question is asking what is the direction. So I need to find this direction, this angle here. Okay, so now I have the opposite and the hypotenuse. So I'm going to use sine 2.5 over 4.5. Solve for sine or solve for theta. I get 34 degrees. So, and I'm going to say she needs to travel 34 degrees, steers 34 degrees upstream. Okay. I don't have any direction, so I'm just saying 34 degrees upstream. Okay, let's look at an example where we are given some direction. So these ones can be really confusing, primarily because they're just hard to read. So we want to be very careful when we're setting them up that we know what's going on. I'm going to start by drawing a few sketches in. This is going to help me set up my question properly. Actually, I'm going to use a ruler. Okay, so I have a compass north, south, east, west. That's going to help me figure out where to draw these lines. So the first thing I'm going to consider is this plane that's heading southwest at a speed of 450 kilometers per hour. Okay, so I'm going to draw a line in here to represent that. And it's going southwest. So I want to change this so that it's pointing southwest. It doesn't give me an angle, so I know that it's going to be 45 degrees. So I'm just going to put that there for now. It's about 45 degrees. Okay, my next vector is this wind that's blowing at 100 kilometers an hour from 25 degrees north of west. So I'm going to get another vector arrow, and I'm going to make it green to match. And it's going 100 kilometers per hour from 25 degrees north of west. So it's 25 degrees north of west, and it's going from that direction. So it's going, it's actually going southeast because it's coming from northwest. So here's my two vectors. And I would start by setting up every diagram like this. So I want to add these vectors tip to tail. And so I need to adjust them. So I'm going to adjust them a bit for size just to kind of make it look a little bit more proportional here. And this guy is bigger than that guy. Okay, so I can either, I can do one of two things. Oops. I can move this wind vector back and move this guy down here. Okay. So I can have a resultant vector between these two, and I can also have this vector down here. Now so I'm going to use either one of these two options. The result will be the same. So I like to keep everything centered about my compass. So I'm going to keep it there. So that means my resultant vector is from here to there. Okay, so let's label some stuff here. So here's my wind. Here's my plane, and here's what I'm looking for. So what I need to figure out is this angle. I know that this is 45 here, and this is 25 there. So I can figure out the total is 70. So now I just use cosine law. The hardest part of these problems absolutely is setting up the diagram, because after you have it set up, it's every time it's only cosine law or sine law. Okay, so solve for cosine law, I get 426. I'm going to just do a little check. Is the wind helping or hindering? In this case, the wind is hindering, so 426 less than 450 makes sense. So because I am looking for a resultant ground velocity, I need to know the direction of this guy here. So what I'm going to do is I'm going to draw another little compass right here in order to help me see what's happening. So I'm going to use sine law to get this angle here. So sine of that angle over 100 is sine of 70 over 426. The value of that angle, when I calculate that out, is 13 degrees. I already know that this is 45. I know that all of this needs to add up to 180, or sorry, excuse me, 90. So that's going to give me an angle of 32 there. So this plane is traveling south 32 degrees west. Okay, one more small idea here. This one's relatively simple compared to that last question, is this idea of relative velocity. Relative velocity is the velocity of one object when you compare it to another. So if you're driving down the freeway at the same speed as another car, your relative velocity is 0. So two objects A and B have velocities, velocity A and velocity B, respectively. If the velocity of B relative to the velocity of A is the difference of those two vectors. So let's just look at a simple example. So a car is heading west at 90 kilometers an hour, and it's meeting a transfer truck heading east at 85 kilometers an hour. What is the relative velocity of the truck relative to the car? And so we're going to add these two up to find the velocity that's relative is 90 plus 85 or 175. We can also look at an instance where the truck maybe turns. So now the truck has turned and it's heading north at 85 kilometers per hour. The car is still going at 90 kilometers per hour. And now my resultant velocity is here. Okay, so I have a right angled triangle, perfect right angled triangle here. So I can just use 85 squared plus 90 squared. Let's root that to give me a resultant velocity of 124 kilometers per hour. And I maybe want to know, because I'm doing velocity, I want to know the direction of travel also. So I'm going to find out the angle here. Opposite over adjacent. Angle here is 43.3. So I have a couple of options. I can say the relative velocity is east 43.3 degrees north, but this is kind of crazy because we usually go northwest first, and then 47 degrees east. All right, practice problems. Let me know if you have any questions.